Welcome to the class on a single phase full bridge inverter. This is a circuit diagram for the single phase full bridge inverter. The circuit is consisting of four control switches Q1, Q2, Q3, Q4. It also consisting of feedback diodes D1, D2, D3, D4. Input voltage Vs, load. This is the positive direction of the load voltage. This is the positive direction of the load current. If the Q1, Q2 is on, source is supplying current from source Q1, load Q2 again return to the source. So load voltage and current is positive. Suppose if the D1, D2 is on, remaining all devices are off. Now the load is supplying current from load D1, source D2 again return to the load. Nothing but voltage is positive and current is negative. If Q3, Q4 is on, now the current is supplied from source Q3, load Q4 again return to the source in this manner. The load voltage and current is negative. Load voltage and current is negative. Suppose if D3, D4 is conducting, the diode is allowing a current only in the anode to the cathode. So load D3, source D4 again return to the load. Load voltage becomes a negative whereas the current becomes a positive. Now we are going to see the circuit operation. First you have to take the input voltage, that is Vs, which is constant with respect to the time. This duration is nothing but T by 2. This duration is nothing but again half cycle and half cycle. From 0 to T is nothing but a one cyclic operation. These are the gate voltages which is applied to Q1, Q2. When the gate voltage is applied, the Q1, Q2 is on. If the gate voltage 0, then Q1, Q2 will be off. These are the gate voltage applied to the Q3, Q4. In this duration Q3, Q4 is on. Again in this duration Q3, Q4 is on. The remaining duration Q3, Q4 will be off. If we draw the output voltage from 0 to T by 2, Q1, Q2 is on, so the load voltage becomes a positive, that is Vs. In this duration Q3, Q4 is on, so the load voltage is equal to the negative, that is minus Vs. The same cyclic operation will be done for the remaining cycle. For the resistive load, the current is in phase with a voltage, same waveform, but the magnitude will be lesser. For the RL load, current lags this voltage, but it is a triangular waveform. 0 to T1, D1, D2 is conducting. T1 to T by 2, Q1, Q2 is conducting. In this duration, T by 2 to T2, D3, D4 is conducting. Again in this interval, Q3, Q4 is conducting. The same thing for the remaining cycles. For RLC underdamped, the current waveform lacks the voltage, but it is a sinusoidal waveform. Again here, D1, D2 is conducting. In this interval, Q1, Q2 is conducting. In this interval, D3, D4 is conducting. In this interval, D3, D4 is conducting. Suppose if you want to find out the RMS output voltage, means this voltage square into T by 2 divided by T by 2 whole root, that gives the RMS output voltage. That value becomes a Vs. This is the output voltage waveform. It is not a pure sine wave. It is consisting of harmonics along with the fundamental. To know the harmonics means you have to write the Fourier series. So this waveform is symmetrical about the x-axis. This waveform does not consisting a even order harmonics. So V naught equal to sigma n equal to 1 comma 3 comma 5 up to infinity 4 Vs by n pi sin n omega t. For RLC circuit, if you apply this voltage, then the current waveform we are getting. Further current waveform, if you write the Fourier series, means I naught equal to sigma n equal to 1 comma 3 comma 5 up to infinity 4 Vs divided by n pi Zn sin n omega t minus pi n, where n is nothing but the order of the harmonics. Zn is nothing but a impedance due to the harmonics, that is Z suffix n equal to square root of r square plus n omega L minus 1 by n omega c whole square. Here we assume that load is consisting inductance as well as a capacitance. Pi n is nothing but a load angle for the harmonics. So pi n equal to tan inverse n omega L minus 1 by n omega c whole divided by r. Suppose if you want to find out the RMS value of fundamental voltage, this is the maximum voltage divided by the root 2 where n equal to 1. So 4 Vs by root 2 pi, we are getting the 0.9 Vs. In a previous class, for a half bridge inverter, the RMS value of fundamental voltage we got the 0.45, but here 0.9 Vs. Nothing but output power will be increases by 2 times. So what is the disadvantages there in a half bridge inverter that we can overcome in case of a full bridge inverter? Moreover, the circuit is only the two-wire system. It does not require say third wire. Thank you very much for watching this video.